The last topic we need to cover on Unit 5, Electricity and Magnetism, is 5.4 Magnetic Effects of Electric Currents. Before we get on to the idea of looking at magnetic effects of electric currents, we're first going to have a look at magnets and magnetic fields. So we need to get a good understanding of those ideas first before we start to look at how electric currents are involved. And to do that, we first of all need to identify what magnetism actually is. And it's simply a property of ferrous metals, and the most common ferrous metal would be iron, but there are some others that will produce magnetic effects as well. And so, like I say, iron's the most common, but you might hear of neodymium magnets as well. The property that we're talking about here is that they will attract other ferrous metals to them. So all of the magnets that you come across, typically they're going to contain some iron, and that means that because they're magnetic, they'll then attract other metals that contain iron, or other alloys. They'll attract those metals to them. And the reason why this property exists, it's due to the alignment of the spins of electrons. So all of the electrons that are in the metal will be aligned, and as a result that produces this property of magnetism. Now, not all iron containing metals will be magnetic, so it's only the ones where the spins of the electrons are aligned. There's lots of examples of iron where they're not aligned, and so they're not magnetic. But they can be magnetized in a few different ways. We'll have a brief discussion about that in class. But the main thing here is that magnetism is just that property where it will attract other ferrous metals to it. There are two types of magnets that I'll just briefly mention here. So the first is hard magnets. Now, hard here doesn't refer to whether or not they're actually physically hard. It refers to the fact that hard magnets retain their magnetic properties. So they are always magnetic. They can be demagnetized in a few ways, and again we'll talk about some of those aspects in class. But hard magnets retain their properties, and soft magnets, and again it's not that the metal is actually soft to touch, it's about the magnetic properties. Soft magnets become magnetized when in a magnetic field, but will lose those magnetic properties when that magnetic field is removed, or when it's removed from the magnetic field. So that idea is quite useful in some scenarios. We'll get onto that in a bit more detail again when we look at magnetic fields produced by currents. So important to distinguish between the two, so that we've got a clear idea of the effects that can occur when we have a soft magnet compared to a hard magnet. So we now need to look at magnetic fields, and they're similar to electric fields in a way, given that fields all have similar properties. Magnetic fields exist around magnets, and as the title of this unit suggests, they also exist around current carrying conductors. And there are a few properties of those fields that we need to identify, and those properties are similar to what we identified for electric fields, with some differences. So the first thing is that they show the direction of force. So a field will always show the direction of force, but in this case it's the direction of force on a small singular north pole. So if we look at a magnet, we know that it has a north pole and a south pole, and if we were to consider the idea of a small singular north pole, we could then identify the direction of the field. Need to make a point here though, that idea of a small singular north pole is very much just a construct to help us make sense of a field, because singular north poles don't actually exist. A singular pole is, like I say, just a construct that we can use to help explain this idea, but you don't actually find them by themselves. They're always in pairs, a north pole and a south pole. So just keep that in mind when we're dealing with these ideas. The second thing then is that magnetic field lines show the magnitude of the force, which we can otherwise interpret as being the strength of the field, and hopefully you can recall that property is represented by the spacing of the field lines. So the stronger the field, the closer the spacing of the field lines. Now, to have a quick look at what magnetic field would look like, let's have a look at two scenarios that hopefully you're fairly familiar with already. So the first one is just a bar magnet, and as we've already identified, we have poles in a bar magnet, so the north pole at one end and the south pole at the other. So if we consider what would happen to a singular north pole, anywhere around the north pole it's going to be repelled, and anywhere around the south pole it's going to be attracted. So our field lines will look something like this. They'll be symmetrical around the magnet, and I'll just try and draw a few of them in. Note that I'm just sketching this rather quickly, so hopefully it gives the idea and represents it fairly accurately. And notice here I'm not bothering to join these ones up, just drawing them so that they represent the shape of the field. Always in towards the south and away from the north. So we can represent the field lines as shown like that. Another common situation that you might come across would be a horseshoe magnet. So horseshoe magnet in that sort of U shape. Sometimes they're a little bit more curved around so that the ends of the magnet are closer together, sometimes further apart. Again though, we'd have a north pole and a south pole at the ends, and so we'd see that characteristic shape again, where the field lines sort of bend out and around out from the north and into the south. And as they sort of come out the sides here, they're spreading fairly far apart, so fairly weak field out to the sides of a horseshoe magnet. But through the middle here, we have a region where the field lines are just about parallel, and so that's an important region to note. So this region here, where the field lines are parallel, we'd identify that as being a uniform magnetic field. So as with electric fields, if the field lines are parallel, that means that the field strength is constant in that region, and so it would be referred to as being a uniform field. So in that case, a uniform magnetic field. Another key point to note about magnetic field lines, or any field line really, is that they don't cross. And the reason why that's important is that it means that the field is going to be unique at each point in space. So we can't have two fields in the same region sort of crossing over each other. Instead, if we had two fields produced by, say, two bar magnets, because they are both vector fields, that means that we can add them together to figure out the resultant field. So in some situations we might have two magnets in close proximity, and so we can add those two using vector addition, and that will produce the resultant field in that region. And finally, the general rule for magnetism, specifically when we're talking about bar magnets, is that we're going to see forces of attraction and repulsion when we have certain circumstances. So if we have like poles, that means they're going to repel. So two north poles that are near each other are going to repel each other, and two south poles would likewise repel each other. Whereas if we have opposite poles, so a north and a south, we're going to see that they will attract. So the basic idea of magnetism there. As I said, in the next video we'll start to look at magnetic fields that are produced around currents, and we'll deal with that in a bit more detail.